So Gibbs free energy and free energy are the same thing. So you could put a G there, and you could put an S there. Oops, sorry, spontaneity. Nope, that's not what I meant. For spontaneity, you could say, does it go from left to right? Question mark. There's no variable for that. Does it go from left to right? Spontaneity. All right, cool. So is this the next slide you have?
No.
Okay. This must just be, it's a slide you're going to see here in a few slides, but it's also a slide that you've seen before. Mother Nature likes to go to chaos. That actually is this one right here, the dispersion of matter. That is increasing S. And Mother Nature likes to cool off. Basically, he or she or whatever likes to disperse the energy of the system. The system likes to give away its energy. And do you remember when we talked about that actually is going to be an H, enthalpy. So if something gives away its energy, that is, we'll be in the library about 3. Something gives away its energy, that is exothermic. What is H? Delta H. Is it positive or negative? It is.
Okay.
Delta H is negative or less than 0 for it giving away its energy. Yeah, exactly. And I'll put delta S is greater than 0 for giving away its matter. So this whole slide, or this is talking about spontaneity. Will a reaction go from left to right? Well, if it's going to give away its energy and it's going to become more chaotic, then yeah, it's going to be spontaneous. So that's basically what we need to talk about.
Oh, well, that makes sense.
I think
Because
so.
you can't spontaneously make a watch come together. And start
Right.
on time.
Right. But if there was an enthalpy term, delta H hiding in there somewhere, you can make it happen. I'll show you how that works. Yeah, it's interesting. So a spontaneous reaction is one, as it's written, from left to right, it will proceed. Okay. Either just a one-way reaction arrow, the reaction will proceed, or if it's not an equilibrium, it will favor the formation of the products. All right. So this is one of my favorite concepts. The next slide is really cool. So if it's not spontaneous, then that means actually it favors the reactants. That means actually it's going to go from right back to left again as it's written. Makes sense? So here's my favorite one. If it's not spontaneous, basically just swing it around the equilibrium arrow. Okay? And then what were your products are now your reactants, and it's spontaneous. I just think that's funny.
So that'd be like an acid-base reaction where it's not going to go to a higher,
Right.
to a strong acid. So you switch it.
Exactly, exactly. And because that's a very good example of spontaneity and fixing spontaneity. Mm-hmm. You got it. So yeah, here finally is the slide that I kind of wanted to start with. Okay, so Mother Nature wants to disperse the energy and disperse the matter. That's the delta H and the delta S term. Okay, so if we want to look at a chemical reaction, we need to know, and to assess it for spontaneity, we need to look at both of those. That's it. So the entropy change of the system, entropy needs to be increasing. Okay, and the energy change of the system, you told me if something is getting rid of its energy, if a system is getting rid of its energy, sorry, it is, the delta H is negative. And you're right, change in energy in the system. So, of course, S is entropy. So if the change in entropy is positive, as greater than 0, okay, then what we've been talking about the last lecture period and today, then that means that it is becoming more disordered. And if the change in entropy of the system is negative, that means it's becoming more ordered, which does not favor spontaneity. Then let's look at enthalpy. So again, this is kind of like a Chem 1 sort of thing. Delta H is change in enthalpy. So if your change in enthalpy is positive, then actually that's an endothermic reaction. Okay? Oh, sorry, it looks like I'm starting down here. If it's negative, less than 0, that means you're getting rid of energy, which is what Mother Nature prefers. Okay, and that favors spontaneity, exothermic reaction. If it's positive, then we've been calling that, if your change in enthalpy is positive, of course that means endothermic, and it's taking in energy, which does not favor spontaneity. So I think I have some slides just to kind of reinforce all that coming up. But before I do, Gibbs free energy is kind of I don't know if Gibbs free energy does anything other than assess spontaneity. I don't know. Gibbs free energy, that G, if it's negative, oops, sorry, must say it here. Okay, so Gibbs free energy. So here's how you calculate Gibbs, the change in Gibbs free energy. You got to look at both the what's going on with energy and what's going on with entropy. And so there you go. This would be one, I think for Unit 5, I give you an equation sheet, and I'll give that, because you'll have some questions over this unit on your final. And I'll give you that equation sheet so you'll know what you're looking at. Cool.
And that temperature, does that have to be Kelvin?
Yes, very good. Has to be units, Kelvin units of Kelvin. So this is what I got ahead of myself. If that is negative, that being the Gibbs free energy, changing Gibbs free energy, if it's negative, then that means the chemical reaction is spontaneous. And if you remember, the delta G is equal to delta H minus T delta S, and if you remember delta H needs to be negative, then you're like, oh, okay, well then my delta G needs to be negative, because delta H negative favors spontaneity. Delta S positive favors spontaneity. That's why then if you subtract something that's positive, you make it more negative. Does that make sense? Okay, very good. Perfect. So, yep, if the change in Gibbs free energy is negative, then the reaction is spontaneous. If the change in Gibbs free energy is positive, then the reaction is non-spontaneous, and then all you got to do is swing it around the reaction arrow to make it spontaneous. And this is kind of an interesting, important thing. We'll be talking more about this. If the change in Gibbs free energy is right at 0, then that means it doesn't favor the forward direction or the reverse direction. So basically, it's at a standstill. It's at equilibrium. Assuming this is an equilibrium reaction, not just a one-way reaction arrow. It's going back and forth at the same rate. Neither side is favored. So we talked about this a little bit ago, that we have this relationship between the change in thermal energy of the system and the change in thermal energy of the... See, now there's another typo. Did I have a typo before? What is this? I swear I didn't change all this. That should be... what does your note say?
Change. Is that a note to yourself saying to change it, or is that something else?
What did...
Does that mean the enthalpy of the phase change?
See, I think... Oh, actually, they're both positive. That's the difference. I don't know. I'll have to confer with my colleague, because I think it should be system because it's not negative, by negative surroundings, but I think it should be system. Because change does not make sense to me. Okay. Oh yeah, that's why. Okay, so, well, not why, but I'm going to kind of show you how we get to this from this. Okay. So we said if it's at equilibrium, Gibbs free energy is 0. Okay. So if Gibbs delta G of the system is 0, then basically the delta S of the system is equal to delta H of the system is equal to T delta S of the system. Okay? And then if we want to solve for the entropy, the delta S, all we got to do is divide both sides by T. And we basically get that. So that's why it shouldn't say change, it should say system. Okay. I think we have a problem coming up. Not quite yet. Okay, so we're going to talk through 4 scenarios. There are 4 scenarios on these next 4 slides. And in each one of them, we are going to evaluate the situation for spontaneity. Is your delta G negative or positive? In this first case, we're going to go with a negative delta H, a negative enthalpy, which favors spontaneity. And we're going to go with, and it's kind of a little bit confusing, but we're going to go with a positive delta S. That also favors spontaneity. And bottom line is, if you have a negative enthalpy and a positive entropy, there's no way you can screw it up. Your delta G is always going to be negative. Makes sense. Your reaction will always be spontaneous. So there's 4 scenarios. That's the first of 4. Well, here's the next scenario. Let's just say that, again, you have an exothermic reaction. Your delta H is negative. But now your entropy is negative. Your delta S is negative. Okay? So this actually disfavors spontaneity. I'll just put spont for spontaneity. Okay. So now it depends. If, down here, I say, if the magnitude, that's the absolute value, if the magnitude of your delta H term, your change in enthalpy, is greater than the product of T delta S, then this guy, your enthalpy wins out, and enthalpy favors spontaneity. Okay? So if this is the case, we say it's spontaneous and it's driven by the enthalpy. We say that because the entropy was holding it back. So it's driven by the enthalpy. Does that make sense? If it weren't for the enthalpy, the magnitude being larger, then T delta S, the delta S term was dragging it down. The enthalpy made it win out. So it's spontaneous. So that was the second of 4 scenarios. The third of 4 scenarios looks like this. Oh, one more thing is this one, notice that this is most likely to be the case if your temperature term, your absolute temperature, if that's pretty small, then the product of T delta S is going to be kind of small. And then it can be enthalpy driven like that. Okay. Here is the third of 4. In this case, notice we have an endothermic reaction. Okay, your delta H, your delta H is positive. It's endothermic. And this disfavors spontaneity. And your delta S term is back to being positive again. So that favors spontaneity. And here again, it kind of depends on kind of their relative magnitudes. So you can get a spontaneous reaction. You can get delta G negative. if the magnitude of your enthalpy term is less than the magnitude of your T delta S. In that case, aside from the enthalpy not favoring spontaneity, the entropy saves the day. So we call that entropy driven. And the higher the temperatures, then the more likely that T delta S term is to be larger than the delta H. Saves the day. So that's the third of 4. Now this is the fourth of 4. In this case, we're going against the grain both ways. Okay? So notice that your delta H is positive. That means endothermic. That means disfavors spontaneity. And your delta S is negative. And that also disfavors. So you're like, it's not going to work. Okay, so regardless of what those values are, okay, your delta G is going to be positive. Your delta G will never be negative. And it won't be spontaneous. Exclamation point. Unless you swing it around the reaction at equilibrium arrow, and then you're back in business. I just think that's so funny. So here's a figure from your textbook doing those 4 scenarios that we just did. So the first scenario, we said that spontaneity was favored both by the H term and the S term. The second scenario, we said that spontaneity was favored by the first, but not the H, but not the S. Okay. And the third one, we said that it was favored by the delta S, but not the delta H. And the fourth scenario, we said it was disfavored by both. Okay. So let's, I think, do some problems I think we have coming up, but not in science lab. So we have some options here coming up with Gibbs free energy, delta G. We can either get it by, if we know delta H, if we know delta S, and if we know the temperature, we can get delta G. Or we can do it kind of like we did delta S a minute ago. We can look up the individual, sum up the products, sum up the reactants, and do subtraction. So we're going to kind of look at some problems, I think. So delta G sub F is Gibbs free energy of formation. That's the script F at standard state. And it's the standard, I guess it's the molar formation of 1 mole, sorry. Okay, so this is kind of neat. So Gibbs, the standard molar Gibbs free energy of formation. It's 0 if you have an element in its standard state at standard conditions. So that's kind of neat. You're going to see some zeros there. So here are some zeros, and you just need to ask yourself, at 25 degrees Celsius and 1 bar pressure, I buy this, hydrogen is a gas, nitrogen is a gas. So for that reason, their standard molar Gibbs free energy of formation is 0. Okay. Yeah. Okay, so let's do a problem. I wanted to get to one of these today. So we could come up with these thermodynamic values for this reaction, as it's written from left to right. And what did I say? Once we come up with delta H, the change in enthalpy, we'll know whether it's endothermic or exothermic. Of course, if it's negative, it's exo. If it's positive, it's endo. Once we come up with, we know the sign of the delta S, we know if it's creating order, be negative, or if it's creating disorder, positive. And once we come up with the delta G, then we know if it's spontaneous as written. Okay? All right. I kind of feel like we've beaten this over. Okay. So there's different ways to look at it. This is all lining up all the pluses and all the minuses. And then remember that a positive enthalpy, yeah. Well, this doesn't give as much information as we've been talking about. Positive enthalpy, we said disfavors spontaneity. Negative entropy disfavors spontaneity. A positive Gibbs free energy disfavors spontaneity. So, okay. So let's just say you had this information available to you and you wanted to answer those three questions, the delta H, the delta S, and the delta G for that reaction. We can do the whole summation thing and knock those three problems out, and I think that's what I do next. Okay, starting with the change in enthalpy. So we're going to look at the product side first, which, again, this is the combustion of methane. So it forms carbon dioxide and water. 1 mole of CO2 times negative 393.5 kilojoules per mole, plus 2 moles of H2O times negative 285.8 kilojoules per mole. Add those together, you get a negative 965.1 kilojoules. And then we look at the reactant side. So the coefficient in front of the CH4 is 1, so 1 mole of CH4 times negative 74.8 kilojoules. Per mole, plus the coefficient in front of the oxygen is 2 moles of O2, and the standard molar enthalpy of formation of something like oxygen here in its standard state, standard conditions, is 0. So that math is pretty easy. So on the reactant side, we have a negative 74.8 kilojoules. So then we have just a subtraction left. So we take the negative 965.1 minus a negative 74.8, and we get a negative 890.3 kilojoules. So what do you think, endothermic or exothermic?
Exothermic.
Mm-hmm. Exo. Perfect. Fine. Okay. 1 down, 2 to go. Yep, it is definitely exothermic. And that would favor spontaneity, right? Okay, let's go for the delta S in a similar fashion. So looking at the products, we have 1 mole of CO2 times 213.7 joules per mole Kelvin, plus 2 moles of H2O times 69.9 joules per mole Kelvin. That gives us 353.5 joules per Kelvin on the product side. And then on the reactant side, that looks like this. 1 mole of CH4 times 186.3 joules per mole Kelvin, plus 2 moles of O2 times 205.1 joules per mole Kelvin. That gives us 596 0.5 joules per Kelvin. Now ready for the subtraction part. So then the delta S is 353.5 kilojoules, joules per Kelvin minus 596.5 joules per Kelvin. So we got a negative 243.0 joules per Kelvin. So what do you think? Creating order or creating disorder?
Sorry, I'm thinking. Order.
Right. Yep, very good. Perfect. All right then, one more. So to me, we have a choice here, and I can't remember what my notes do. We could take the delta H and the delta S we got and plug them back in, or we could do the summation thing since we have the individual G's for everything. Now it looks like we're going to do the latter, or the former. Okay, so a little bit ago, we came up with the delta H, the enthalpy change is negative 890.3 kilojoules. And more recently, we came up with the delta S as negative 243.0 joules per Kelvin. Now, hopefully you're looking at, oh goodness, my energy units need to be in agreement here, and you're right. So I think I go to joules. But the other thing is the temperature. You get the temperature, don't let this throw you off, from actually the fact that there is a knot. Yeah, so, but you have to take 273 plus 25 to get the Kelvin temperature. Yep. So the temperature is 25.0. I'm not sure why the 25.0. 25.0 plus 273.15. So the T here we're going to use is 298.2 Kelvin. And then, like I said, we got to make sure the whole kilojoules and joules things is fixed. So here we go. Delta G is equal to delta H minus T delta S. So delta G is equal to negative 890.3 kilojoules. That's our delta H term. Minus the T we came up with was 298.2 Kelvin. And that's T times S. So then these last two terms here, okay, basically convert from joules to kilojoules. So this was our delta S was negative 243.0 joules per Kelvin. And I need to get it in kilojoules because I have kilojoules here. So this needs to be in kilojoules. Times 1 kilojoule over 1,000 joules. So factor label-wise, notice that units of Kelvin cancel, units of joules cancel, and we actually have this term over here, which is subtracted from this term, is actually in units of kilojoules, which is perfect. Drum roll. I couldn't remember what it was. So we have a delta G change in Gibbs free energy of negative 817.9 kilojoules. So what do you think? Is it spontaneous?
Yes.
Yes, it is spontaneous. Ding, 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 ding. Perfect. Okay, and remember we talked about this, since the entropy is kind of going against the buck, but the enthalpy is going with the buck or whatever, then the fact that it is spontaneous is enthalpy driven. Let's see, is there more than that? I guess, okay, I don't know why this is so dramatic. But yeah, so this favors and this disfavors.